So Ben, good morning, and the floor is yours.
Thanks, Seth. Good morning, everybody. This is going to be kind of an interesting experiment here on how this all works. I'm going to try to make this pretty interactive, and that's kind of the point of this Sharpen the Saw training. But before we get to that, I'm just going to kind of give a quick rundown of kind of what we in the SWIP are envisioning with this Sharpen the Saw training, what it is, that sort of stuff. I promise I didn't dress like a lumberjack on purpose today for the Sharpen the Saw training. It's just kind of how I often dress, as my staff pointed out to me today. So with that, let's go ahead and kind of talk a little bit about what this is. So the concept of sharpening the saw comes from Stephen Covey's 7 Habits of Highly Effective People, and sharpening the saw is his 7th habit, and he introduces it like this. Suppose you were to come upon someone in the woods working feverishly to saw down a tree. What are you doing, you ask? The person says, can't you see? I'm sawing down this tree. You look exhausted, you exclaim. How long have you been at it? Over 5 hours, he returns, and I'm beat. This is hard work. Well, why don't you take a break for a few minutes and sharpen your saw, you inquire. I'm sure that would go a lot faster. I don't have any time to sharpen the saw, the man says emphatically. I'm too busy sawing. So put a little bit differently, we tend to become pretty ineffective or inefficient if we don't take time to refresh our tools, or when it comes to convective warnings, when we take time to refresh our skills or understanding of severe thunderstorms. And that's kind of what we're trying to do with these trainings, provide relatively short, self-paced, interactive trainings so people can actually spend some time sharpening the saws, sharpening their skills and understanding of how these works. So we've got a few different sharpen the saw exercises that we've either put together or in the process of putting together. That includes radar case walkthroughs, and that's what I'm going to be talking about today. We've also got a few follow-along videos that are put together. So these videos are going to have, they're narrated YouTube videos, but they're going to have kind of built-in pauses for people to stop and kind of make their own assessment of what's going on. And then another, big effort for our team are these RSIC cases. And there's been a handful of these innovation spotlights talking about RSIC, but we're trying to figure out ways that kind of the SWIP can utilize that to also provide training to people. But for today, we're going to be talking about these radar case walkthroughs. And there's going to be relatively detailed instructions that'll be emailed to all Central Region SUs and all and SWIP liaisons. And it's also going to be added to the SWIP Google page. We haven't done that quite yet because they're just about finalized, but I want to make sure all of our T's are crossed and I's are dotted. But essentially the basic workflow for these radar case walkthroughs is first you're going to access the Google form for the case. That Google form is going to contain instructions that you'll follow to download radar data, load the data into GR2, and access the supporting documentation. You'll continue to step through the form, answering questions about the radar data, and finally you'll submit the form and view feedback within the form. And so with that, what do you need? Well, basically just internet access and GR2. And so what I'm going to do today is kind of walk through what the process is going to look like from getting the form, accessing the data, loading that data into GR, and then we'll actually go through a case. And so this is kind of meant to be twofold here today. First, it's just to show you how this training works. Second is to talk a little bit about an interesting case that we had here in St. Louis. So for those of you that are on a computer that does have GR enabled, you're welcome to kind of to follow along. And so before we do that, though, I do want to point out that so what I've got a link here, and I'll put in the chat for this for the chat room, is the link to the master Google Forms. It should be set that you all can view them, but cannot, adjust them, which is ideal. And what you'll want to do is each office should make a copy of the master form for each case. This will allow you to change some of the settings within the forms, make minor tweaks to verbiage, etc. For example, the way it's set up by default is that all exercises are going to have a quizzing function that's going to give meteorologists scores based on their answer. You may want to change these settings for one reason or another. And so by making a little copy of this, it'll give you an ability to do that. The good news is when you make a copy of the master form, all of the links to data and documentation are still going to point to the CWIP folders, regardless of where you store your local copy. So this should all work. I've tested it as best I can, and I guess we'll see, get their hand on them, whether or not they have access to the data. So I'm going to open this up and I will post a link to this in the chat room here so people can access it if they're interested. And you'll have to forgive me as I'm going to be juggling between a whole bunch of different screens here, and I can only share one with y'all, and so I'm going to try to make this work as best I can. So the first thing I want to point out is just this instructions document. And this pretty well just talks about what I already talked about in the slides. It talks about the general workflow of the case. It talks about how to create copies for your office. It goes through the same kind of disclaimer I gave about making a copy of the master form, and then it's got a list of the cases that we've put together. Right now we've just got two. The first one is from my office. It was put together largely by one of my senior forecasters, and I had a little bit of input of that as well. And then we've got a case from Springfield that was put together by Jason Schauman, the Sioux down there, and a couple of his meteorologists as well. And the idea is, especially if people kind of take a liking to these, is we'll continue to add onto this case listing and provide more and more of these opportunities for people to continue to sharpen the saw. So we'll go back into this document, and we're going to look at the St. Louis case today because that's the one that I'm the most familiar with. We'll come in here, and I'm going to open the master document, and I'm actually going to move that off to the side because that's not ideally what you're going to be seeing. So let me open just what the form is going to look like. Hopefully what you all can do is just the same as what I did. If you get, actually, I'm guessing when you click on it, you'll probably just get taken straight to what the form looks like, not the master form. So you need to make a copy. Anyway, so this is what the form is going to look like. And the start of each one of these is going to kind of give a brief description of what these radar case walkthroughs are designed to do. So here this says, they're designed to step meteorologists through radar data and severe weather cases, highlighting important features in the warning decision process. Radar case walkthroughs utilize GR2 analysts to interrogate radar data and will typically include additional information provided through the slide decks. This exercise features a supercell that developed in East Central Missouri in 2024 and was developed as part of something that the Central Region Southeast Sioux have been working on. So before you start this exercise, you'll want to obtain the SWIP supercell interactive worksheet for your respective office. And then you'll also probably want to have the supercell-based tornado genesis radar feature guide handy. And so this is a link directly to something that we at the SWIP have distributed across the region. So you'll simply click on next. The first step is just to get the radar data. So I've got the radar data downloaded in a folder that is connected to this case. It's already zipped up, so you can go to the folder. The zip file is right here, and you can just download the data. So we'll do that. And normally, I'd try to have this ready to go for this presentation, but just kind of in the interest of sort of showing off what this is doing and how it's going to work. I want to kind of go through the whole process to show you all what's going on here. So it's downloading the data. Because the data is already zipped, this shouldn't take too long. And then once it's done, we'll go ahead and open that folder, unzip it, and load it into GR. The idea with these is to be relatively quick to hold people's attention, but to also get them kind of interactively working with the data and sort of thinking about what's going on. So we've got it in our downloads here. I'm going to go ahead and delete the copy that I did of this yesterday to test it. We're going to extract it as soon as I can get this all set. We'll just kind of go with the defaults there. It's extracting. It's not taking too long to do this. And then we'll go back here. So we downloaded the radar data. Now we're going to load it into GR. I've got GR open. So we'll find where I put that. And that should be in my downloads directory. There it is. And we've got about 2 hours worth of data here. And so we're going to load this in. So again, we're just kind of waiting for this data to come in. Hopefully it doesn't take too long here. And our storm of interest is going to be kind of right here through the heart of my forecast area. And it's a supercell that moves through and actually into the St. Louis metro area. While that's loading, I will go back to the form. So a couple of other things we're going to need to do in GR once it is all loaded in there. First, I ask people to not examine radar data until you're directed to do so, because it's meant to kind of step you through like you would be in morning operations. And then also turn off LSRs, warnings, and hail icons. And then finally, we're going to set the storm motion to 258 degrees at 32 knots, just so the SRM is correct. So what I'm actually going to do here is have my screens kind of split like this. I know it's not ideal for looking at radar data, but just in the interest of having both the form and GR2 up, we'll be able to kind of see what it is that we're dealing with. And so this is loaded. We'll bring this over here. So my LSRs are, oh, okay, I turned them off. I should have all of my warnings off. And the last thing I'm going to do is set storm motion. You can do that with this arrow right here. And I said to set it to 258 at 32 knots. So SRM should be ready to go. And then we'll go ahead and hit next. So first thing we're going to do is a mesoscale review. Our storm of focus is over Montgomery, Warren, and St. Charles counties in Missouri. That's just west of St. Louis. And so that's this storm over here. And then I asked folks to please examine the environment in this area in this mesoscale briefing slide deck. And just remember that we'll be making warning decisions between 20 and 21 UTC. So we'll click on this link and this slide deck pulls up. For now, I will pull this out separate so it's a little bit easier to see. We'll do a slideshow. And we'll just do kind of a quick review of what's going on. For those of you unfamiliar with my neck of the woods, St. Louis is right there at the red star. And you can see that this storm is just on kind of the warm side of a pretty sharp cape gradient, but certainly of mixed layer cape, really not much capping. And we saw that we already have convection ongoing and it looked like a pretty robust storm. And so that's not really very surprising. And it doesn't change much between 20 and 21Z. 20Z LCL heights are right around 1,000 meters. As we go forward to 21Z, maybe they increase a little bit. So we're perhaps getting a little bit high for tornado genesis, but it's certainly not so high that I would completely rule them out. It's definitely on the higher end, but I feel like tornadoes are doable here. Our 0 to 1 kilometer shear is around about maybe just below 20 knots. And it seems to have gone down just a hair between 20 and 21Z. Our 0 to 1 kilometer SRH is not particularly impressive, generally less than 100 meters squared per second squared, and it's the same deal at 21Z. Our effective storm relative helicity is also not particularly high at 20 or 21Z, and then our effective bulk shear is actually quite a bit higher, so the storm's certainly got access to plenty of deep layer shear where we're in excess of 60 knots or so in the area of interest, and that kind of holds true through 21Z. And then finally, our effective significant tornado parameter is certainly not negligible, between 1 and 2, right around 2 perhaps in the area of interest, and it kind of stays right in that area between 20 and 21Z. So we'll get out of this slide deck. We'll go back over to our, let me do this real quick. We'll go back over to our form and we will start answering some questions. So the first question is, after looking at the mesoscale briefing slide deck and referencing page 2 of this WDTD warning workflow document, or preferably probably your office's own tornado environment reference, this would be another instance where it might be beneficial if you make a local copy of this that you can link your own tornado environment reference. I just tried to find something that was ubiquitous for all offices. Is the near storm environment conducive for tornadic supercells? And I kind of give 4 answers that you can choose from. And what I'm going to go ahead and say is that parameter magnitudes are conducive for supercells. Obviously, we've got plenty of instability, plenty of deep layer shear, but only marginally supportive for tornadic supercells. Our 0 to 1 kilometer shear is kind of right around that magic threshold of 20 knots, maybe just below. And some of the storm relative helicity parameters weren't particularly impressive. So rather than saying parameter magnitudes are conducive for tornadic supercells, I'm just going to say conducive for supercells and only marginally supportive of tornadic supercells. So we'll hit next, and we'll go to our first warning decision. And so what I ask folks to do is examine the radar data between 2020Z and 2040Z across Montgomery and Warren counties in east central Missouri, west of St. Louis. And the first question is, which storm or radar features persist as the storm moves from Montgomery County into Warren County between 2020 and 2040Z? So I'm going to go ahead and move forward to 2020. And so here's our storm of interest. And there's, certainly some interesting things going on here. It's got kind of a classic supercell look to it. There is clearly a hook echo on there. And as we go forward in time, that hook echo persists. There's certainly a little bit of rotation here on the half-degree scan. Nothing super impressive, but rotation nonetheless. probably some side lobing going on out here in the forward flank of the storm, where we can see these really high inbounds. If we go up, there are indeed some higher echoes above that, so that tells me that probably is a little bit of side lobe contamination. Looking down here at ZDR, we can see in the forward flank, especially as you get back closer to the hook, our ZDR is really quite low, and that is a good indication that there's probably some large hail going on in here. And it's not until you get way out into the forward flank downstream of the hook that you start to see the higher ZDR that would kind of lead you to believe that there's some side sorting going on here in the storm. We'll continue to push forward to 2040Z when we're making our quote-unquote warning decision. And it looks like the ZDR arc kind of gets its act back together. It really extends back toward the hook and where the updraft is at. But that's a pretty it's not a very persistent feature as we go through this 20-minute period. So we're going to go over here and start answering what we've got. Well, we clearly have got a hook echo. Certainly, I don't have a correlation coefficient turned on here. But I will turn it on, and as you might suspect, given the very weak rotation that we're looking at, there's really no clear signal for a tornadic debris signature. There's certainly some lowering in the correlation coefficient here, but it's co-located in areas of very low reflectivity and also areas of low differential reflectivity, so certainly nothing here that I would call a TDS, so we'll say not persistent. Low-level mesocyclone, there is definitely some weak rotation that kind of persists throughout the storm. I'm just tilting up here, and you can see that rotation is hanging around, and there'll be a future question about the mesocyclone here coming up, but there is certainly a bit of a mesocyclone. We'll switch back to KDP over here, and well, there certainly is a KDP foot. We've got the relatively high values of KDP co-located with, or more or less co-located with our very high ZDR, so we'll say KDP foot. We did see some side lobe contamination on at least one scan, but just kind of the way that some of these features evolve and the way we want to try to highlight some of the things going on here, just because it was there for one scan, I'm going to go ahead and say that it's not persistent. And that is the reason we kind of decided to word these as present or not persistent is the way the ZDR arc behaves. I had some discussions with some of the folks on the SWIP about how to kind of handle this. And there's a few folks that made an argument that especially early on in this loop, it's really hard to say that there's really any ZD arc here because it is so disrupted by this very low ZDR that's back near the updraft. And so there are certainly scans where the ZDR arc kind of comes and goes, and especially as you get to 2040, the end of this time period, you could certainly make a case that there is a ZDR arc, but we're going to go ahead and say that it's not persistent. And I realize that's a little bit confusing, but unfortunately, a lot of these radar features are pretty subjective. And so you'll see as we get to the end that there's an opportunity for people taking this form to get some feedback. And I try to be as explicit as I can be, kind of describing why I provided the answers the way I did. And then finally, I ask if there's a left flank velocity enhancement, and it's quite subtle, but there is actually on the backside of the storm here, hopefully you can see where my mouse is at, a lowering or a valley in the storm relative velocity. And so to zoom out and kind of give you an idea of where the radar is at, you can see we're almost immediately west of the RDA. And this left flank velocity enhancement would, as you would expect, is going almost perpendicular to the radar beam. And so rather than showing up as a velocity enhancement, it's actually going to show up as a lull in the velocity. And as we go back in time, you can actually see that I guess the signature weakens, but what we're actually looking at is probably an intensifying airstream kind of coming down toward the hook. And so we do actually have that left flank velocity enhancement going on at this time. Scrolling to the next question, and we're going to be looking specifically at the 2040Z scan. And I also mentioned that given that the base of most low-level mesocyclones is best found in that 1 to 2 kilometer layer, what are the ideal radar elevation angles to appropriately sample the mesocyclone in the storm over central Warren County? And so part of this is to get people thinking, like really thinking about what they're looking, but it's also to highlight a feature in GR where if you hold control, you can see what the elevation of your scan is. And you can see our half-degree tilt here is only about 1,600 feet or so off the ground. That's probably below where we're going to be looking for the mesocyclone. We tilt up to our 0.8. We're more like 25, 2,600 feet. And it's not until we get to our 1.3 degree tilt that we're solidly in that 1 to 2 kilometer layer between 3,800 feet and 4,000 feet. And then we tilt up again, and we're again around 5,000 feet. So we will say that it is our 1.3 and 1.8 tilts are ideal. There's certainly rotation worth looking at in the low levels, but that's where I'm really trying to find where that the low-level mesocyclone is going to be, is between 1.3 and 1.8. Okay, next question. If there is a mesocyclone, what is the maximum rotational velocity at 24 or 2040 UTC? So we're going to go back to that 1.3 degree scan, and we'll show off another feature of GR, and we're going to measure what our rotational velocity is. The first thing I'm going to do is try to figure out if this highest inbound is co-located with high enough reflectivity to trust, and it probably is. Our reflectivity is around 25 dBz there, so we'll go ahead and count that. We'll put a storm, place a marker there, and then we'll measure rotational velocity. You can see there it says VROT, generally less than 20 knots. And that's even kind of picking the very highest pixel of inbounds there. So we're going to say it's generally between 10 and 20 knots. Zoom out a little bit more to go on to the next question, and we'll go back down to the low levels. Looking at the scan at 2040 Z and referencing the Z and ZDR screenshot below, hopefully you can see that all right. What area is the ZDR arc? And so I've kind of got an area up here on the north part of the storm as area A with some higher ZDR there, an area of higher ZDR back toward the rear flank, and then a area of higher ZDR along the forward flank in area C. And so if you know how to identify your ZDR arcs, they are generally going to be on the forward flank of a supercell where that size sorting is ongoing. So we'll go ahead and say area C is where our ZDR arc is at. So now I'm asking folks to go back and kind of re-examine how the look at the ZDR arc at 2040 Z and ask if there's an area of low ZDR slicing through the ZDR arc. Certainly if you go back to the last several scans, that there's absolutely a very low ZDR that's kind of interrupting that ZDR arc. As you get to 2040, you can make an argument that it has kind of reestablished itself. If you zoom in, there is still some lower ZDR that's kind of working in toward near the updraft. And that's really what we're trying to think about when it comes to ZDR arcs, is whether or not we've got some really cold when we're looking for ZDR arc disruptions, we're trying to see if there are some very cold downdrafts that may be sort of interrupting the updraft, cutting off the updraft, interrupting the tornadogenesis process. And so at this point, I would say that there's still low ZDR slicing through the ZDR arc. And then I ask, so the next question is to examine the ZDR arc at 2040 and see if there's a ZDR arc disruption primarily composed of dry hail. And the way we identify that, and that goes back to one of the SWIP references that I pulled up earlier, and I know this is going to be impossible to see. I'll try to blow it up, see if that helps. So ZDR arc disruption, as we come over here, so if we've got 0 or negative KDP within the disruption, it infers that it infers that there is a dry hail region that may not significantly add negative buoyancy. So tornadogenesis is possible despite this disruption. Well, we'll come back over here and we see that where this disruption is at, kind of right here, I mean, first of all, we just don't have a whole lot of KDP, but when we do get kind of back into where these higher echoes are at, our KDP remains relatively high. It's certainly not near 0 or negative. And so we will say that no, the ZDR arc is composed of wet hail and a mixture of wet or dry hail. And so all of this is hopefully leading people to believe that there's probably a pretty cold downdraft coming down at this point, and may preclude tornadogenesis, at least in the very near term. Another thing that we're trying to highlight to people is looking at separation vectors between ZDR arcs and KDP feet. And so the next thing we're trying to do is get them to identify where the KDP foot is at. So very similar to the exercise or the question with the ZDR arc, I highlight 3 different areas. Up here, area A, kind of out here way downstream, kind of beyond the forward flank even, is area B. And then area C is more back toward the forward flank, and that is indeed what we're calling the KDP foot. And then finally, I'm asking folks to identify what the separation vector storm motion orientation angle is for the KDP footprint and ZDR arc. And so, you know, in real time, hopefully we've got the SPORC algorithm running, and so it can identify these areas for you. But there's also ways you can kind of quickly sort of estimate where your KDP foot and ZDR arc is. So what I'm going to do is in the bottom right portion of my GR, I'm going to place a marker right here that's more or less the centroid of what I'm calling my KDP foot. And then I will, on my right, I've got this center marker. I'm going to kind of put that in the roughly centroid of my ZDR arc, probably something like that. So we've got a separate, an angle between the ZDR arc and KDP foot that is basically from the west northwest to the east southeast, and we're going to zoom out and see how that compares to storm motion. And it's certainly not parallel. The storm is going a little bit kind of north of east, but there's really not a lot of separation between those 2 vectors. Again, a lot of subjectivity here, and so we tried to have the answers be a lot of wiggle room essentially. And in this instance, we could certainly say it's less than 45 degrees. And it's once you start getting more than 45 degrees that there's some indication that the storm may be ingesting additional storm relative helicity. That does not appear to be the case here. And then finally, we're still on this first warning decision. We've actually got to make the decision. So based on your answers above and additional analysis from the storm from 2020 to 2040 Z, fill out your office's SWIP tornado genesis worksheet, and then what warning recommendation does it give you for this situation? So I'm going to pull that up real quick from my office, and if you are not familiar with this sheet, hopefully when I get it up here, you'll understand why you want to have your own copy of it. So bear with me one second. I should have had this up. I should be able to find it pretty quickly. Go to this often enough. Here we go. Bring it over here. So essentially the way this sheet works is you are able to click on and off what's going on here. So we decided that the ZDR arc, you know, maybe let's say for the sake of argument that we'll say right at 2040 there is a ZDR arc there, so we can turn it on. But then we ask, is there low ZDR slicing through the arc? Well, yeah, we'll say that it is. If the previous check shows a ZDR arc disruption, is it composed of dry hail? We said it was not. Is the separation vector angle offset from the storm motion vector by greater than 45 degrees? It is not. Is the LFVE evident? It is. Is the LFVE surging beyond the low-level mesocyclone? I would say probably not, and we'll get a better look at that on the next warning decision. Low-level V sub R greater than 30 knots? It is not. Is the storm depth max VR greater than 30 knots? Well, we didn't look at that, but we can kind of take a look, and as we get aloft, way up here, we can see, place a marker there. It's probably right around 30 knots, but it's certainly not greater than 30 knots, so I wouldn't turn that on. Is there a hook echo? Yes. And is the 0 to 1 kilometer effect, SRH greater than 200 meters squared per second squared? And it was not. So at this point, it is not recommending that we include any tornado warning in our potential warning. You know, we don't get into, so this exercise is mainly focused on kind of tornado warnings. Hopefully there are some pretty obvious signatures here that we would need a severe thunderstorm warning, be it the very high ZDR, the impressive hail spike, the hail core that's got 60 dBz up to almost 30,000 feet. Pretty obvious severe thunderstorm warning here, but in terms of tornado warning, this worksheet is not recommending that we include any sort of tornado wording. Just to kind of highlight how this tool works, we can change a couple of these adjustments. And so just by turning off the fact that there is an area of low ZDR slicing through the arc, you can see it immediately recommends that we go straight to TOR. We can turn some of these other off and maybe it'll recommend severe with TOR possible. But it's that ZDR arc, that very cold downdraft coming down through it, that is pretty much telling us that this storm's going to have a really hard time producing a tornado. So we'll go back to our slide and we'll say that there's going to be no mention of tornadoes in the wording. That's kind of an awkward way to word that question, but nevertheless, we're just trying to kind of get people to think about what they might be doing in this situation. So we'll hit next, and then we're going to do it all over again and look at everything from 2052 to 2106. Now, I mentioned earlier that this is ideally meant to be gone through relatively quickly, and I'm hoping it's just because I am talking my way through it right now that it's taking me a little bit longer than I would like it to for your forecasters to go through and do this. But we're going to do pretty much the exact same thing. We're going to look at it from 2052, which is where I'm at now, to 2106, which is here as it's getting pretty close to the radar. And we'll kind of go back and forth. I'm going to try to get it all on the screen at once. Back and forth. And then we'll sort of reevaluate everything. So is there a hook echo? Very obviously, yes, there is. I'll turn CC back on over here, and we'll try to identify if there's any sort of tornadic debris signature. And as you may suspect, there is not. The only lowerings of correlation coefficient are way out in the clear air, so some sort of non-meteorological target, but certainly not debris. So we'll go back to the end of the scan here. We'll say no TDS. I'm going to turn KDP back on because we're going to want to look at that here in a second. Low-level mesocyclone. So if you look through the depth of this storm, there's really not much rotation anywhere. At this point, I'm up to 7,000 feet, so sort of well above that area. So I'm going to go ahead and say that there's not much of a mesocyclone, at least in the low levels, evident on this storm. KDP foot, yes, there is. You can see very high KDP out here on the forward flank. Side lobe contamination, I didn't see anything that really stood out to me, especially scan over scan. I guess there probably is a little bit of side lobing happening right here, but it's nothing too crazy. So we'll say no side lobing. ZDR arc. Let's see, as we go back to the start of the area time of interest, there's another really obvious disruption in the ZDR arc back here. As we go forward toward the end of the period of interest, you can make an argument that maybe the ZDR arc gets its act together. Again, this is one of those subjective ones, and I honestly can't even remember where we landed on for the correct answer to this. I think probably the right answer, the way we've got it worded here, is not persistent. And then finally, is this LFVE present? Again, we're looking for this airstream kind of on the back side of the storm as we go forward in time. You actually do see it kind of showing up nicely here with these inbounds. And as the storm starts to get a little bit more north of the radar, it actually shows up quite a bit better. Instead of just being a lull, you can actually see those inbounds coming around. And so we will say that the LFVE is present. Same question as above, looking at the 2055 scan, and given that the low-level mesocyclone is best found in the 1 to 2 kilometer layer, what's the idea elevation angle to find that? So again, we're going to be looking for about 3,000 to 6,000 feet or so. So as I tilt up to the second tilt, we're only at 1,000 feet. Third tilt, we're at about 1,500. Fourth tilt, we're getting closer, like 2,300 feet or so. And then finally, when I get up to the last tilt, or the fifth tilt, I think, so I think we're at 2.4. I've got some of the things I normally look at turned off right now, so I'm actually struggling to remember what exactly tilt I'm on. But now we're finally in that kind of 3,000 foot layer. Real quick, I'm going to turn something on so I can actually understand what I'm looking at. So now we're up to 2.4 degrees. And so that's probably the best one. And we'll go ahead and say not ideal for the rest of these because they're probably sampling below where that low-level mesocyclone typically develops. And again, not much signature of rotation at that point. If there is a mesocyclone at this time, how intense is it? And again, we said no mesocyclone, and so we are not going to give an answer there. How would you describe the ZDR arc during this period? And as we mentioned earlier, I'll go back down to the low levels. There's certainly a disruption toward the beginning of the time period of interest. It kind of gets its act together a little bit better toward the end, but as a whole, I would say that there is a disrupted area of low ZDR slicing through the higher ZDR. Is it composed of dry hail, or in other words, Is the disruption have 0 or more negative KDP in it? And that is not the case. We've actually got pretty high KDP all throughout that disruption. So no, the ZDR arc is composed of wet hail and a mixture of wet or dry hail. What's the separation vector between those two areas and the storm motion? So we'll kind of do the same thing. I'll place a marker in the middle of the KDP foot, a marker in the middle of the ZDR arc. And again, just quick and dirty, we're almost due east with that vector. Storm motion is just barely north of east, and so certainly less than 45 degrees. If there is a left flank velocity enhancement, how would you describe it? So the choices are there is no LFVE. The LFVE is beginning to curl toward the mesocyclone, or the LFVE is surging past the mesocyclone. And so we'll take a closer look at this kind of area of green, and we'll go back and forth in time. And this is another signature that it's a little bit more subtle, and I'm certainly just becoming comfortable with assessing myself. But a lot of times what we'll see is this will start to kind of curl back in toward the hook, and it doesn't really seem like it's doing that. And so for the purposes of this, I'm going to say it's surging past the mesocyclone. And then based on your answers above and additional analysis from the storm, fill out your office's tornado genesis worksheet and what recommendation does it give for you. So I'll switch back over here, and I don't really think there's actually anything different from the last time that we filled this out. And so again, the warning recommendation is to not include a tornado warning, or I'm sorry, not include any mention of tornado in the warning. So we'll hit next. So we finished it. And there are a couple of different ways that people can get feedback from doing this. First of all, I provide some slides that kind of walk through the different warning decisions and talk about some of those features that I was highlighting. So as we get to kind of warning decision 1, you can see some of the things I'm talking about. Hook echo, mesocyclone. So on this 2040 scan, there was that ZDR arc, but while it's present at this time, it's not persistent through the time period we asked about. And there's the KDP foot. Here's kind of a highlight of how that ZDR arc disruption evolves. So the idea is that once people finish this and they see what their answers are, they're going to be able to kind of understand why they got the question correct or incorrect. Here's the slide that kind of highlights how I identified the separation vector between the ZDR arc and the KDP foot and how it compares to storm motion. Here's where we go to warning decision 2, kind of look at some of the same things that we talked about as we were going through here. Another kind of 4-scan description of how the ZDR arc is disrupted. Another description of the difference between the storm motion vector and the separation vector, and then kind of a rundown of what happened. And this was an instance where we actually had numerous 2.5 to 3 inch hail reports all along I-70, right into the heart of where some of the people in our office live. We actually had one of the meteorologists in our office is actually sitting close to me right now, had some pretty significant damage to his truck. And then we all followed suit with that last Friday. So now our parking lot looks like a used car dealership or a junkyard, maybe, with all the hail damaged cars. As we get out of this, there is another play. So we can, once you submit it, it's going to score your answers. Let's see how well I did. I think so I actually missed 2 questions, and I think I probably know which one it is. So for a handful of these questions, I was able to put feedback directly into this form. And so it kind of describes why I gave the answer that I did. Unfortunately, the way that Google Forms works, if I have a question that's like this, and I can't remember what exactly setting it is, but basically where I have checkboxes with a bunch of different rows and columns, I cannot provide feedback directly in here. That's why I made the slide deck that we just went through. Again, I talk about kind of why I answered these the way I answered them. And so we can go through. Let's see which question I got wrong. And I think it's, yeah, whether or not there's a ZDR arc here. And there's some back and forth with some of the folks on the team about whether or not we should say that that's a ZDR arc or not. And that's why I got that wrong, because I honestly couldn't remember what we settled on. Oh, it looks like I missed, could have gone with 1.8 degrees to identify the low level mesocyclone as well. And so that's pretty much it. Again, I've got an opportunity where people can click the case review here as well. And so this is one case that we put this together for. As I mentioned, there's another one. It's a QLCS case out of Springfield. Because someone different put that case together, the main thing, the main difference between this case and that case is rather than slides to do a case review, most of that review is actually a video that I think Jason Schauman put together. But that's going to be available for folks in your office to go through as well. So with all that, I feel like I'm out of breath, but I will go ahead and wrap up, and I'd be happy to take any questions or comments that folks have got about what we were talking about here today.
Thanks so much for that, Ben. Awesome demonstration walking people through that with a lot of complex windows on your part there, managing all that. That was a great job showing the front end process of this demonstration. So anybody have any questions or comments for Ben?
While people are thinking about their questions, the biggest reason I wanted to review this case is you can kind of see how my office handled this. I don't think I was on the warning desk, but I'm almost certain I was the warning assistant. So I was sitting right next to the warning forecaster. So I had a lot of involvement in these warning decisions. And you can see we indeed did have a severe thunderstorm warning on the storm for a while. And then as it got closer to the metro, we ended up going with the tornado warning. I think we probably overestimated the environment a little bit. And we still, and I guess I should say, I was still kind of getting comfortable with using things like ZDR disruptions to help me decide, should I go tornado, should I go severe possible? And so we actually did hold on to a tornado warning all through the metro on the storm. That was probably not necessary. Ultimately, we were going to have probably a destructive severe thunderstorm warning on it, so we still would have been WIA-ing people's phones, but I do not think that a tornado warning was the appropriate decision going through here. And just given how the storm looked right now, like at this scan, you know, first glance, you could say, oh, it's a supercell with a big old hook on it. That probably needs a tornado warning. And that's more or less what we did. And kind of the point of this exercise is to highlight, well, we can look at some things that maybe could help us make better decisions. So.
Thanks, Ben. Anybody have any questions for Ben about this setup? It's really a great demonstration of, you know, the WES is so valuable as a training tool, but this can be done short and tactical and targeted and really reinforce some of the SWIP methods and science. So really nice alternative to a full-blown WES case that you've developed here. So that's great.
Yeah, and so if y'all, if these start getting utility and people think that they're useful, we'll go ahead and start making additional cases. I will say that they are a little bit time intensive in our end to make, but if they're useful for people, we're happy to do it. Of course, you know, caveat for us goes with everybody else. I think most of the SUs that we have on the team are also AMICs, and of course, you know, the METs that are on our team are also quite busy with shift work and short staffing and all that. So we're going to try to get these cranked out as fast as we can if people like them, but they may take some time to get them done.
Yeah, absolutely. Last call for questions or comments to Ben.
You must have done a great job.
Yeah, you did indeed. All right, well, we'll go ahead and end the recording. And thanks so much, Ben, for demonstrating this for us and for everybody who took some time to be on the Innovation Spotlight here this morning. Have a great rest of your day and take care, everybody. Hang in there.
Great, thanks.